Okay. Let's just give it, we'll give it 30 more seconds or so for just folks to trickle in. Antonio, if you could just tell me if you can hear me.
Yeah, I can hear you.
Okay, perfect. Well, then in that case, let's go ahead and get started. So, hey everybody, thank you for joining and attending. Today we have a great seminar with Antonio Viggiano on complex and advanced fuzzing mechanics, using practical examples from a case study of applying an effective fuzzing setup on the eBTC protocol. Antonio is going to explain how it was used to confirm vulnerabilities for manual security reviews, finding novel vulnerabilities, and better understanding system behavior under different scenarios. A quick background on Antonio. So he's an independent security researcher who began working in crypto in 2017 as a co-founder of an exchange. In 2021, he founded a gaming company within Web3. And 2022 shifted his focus to blockchain security. Since then, he specialized in property-based testing, pioneered a platform for fuzz testing, and collaborated with many leading protocols to enhance their test suites. And yeah, without further ado, Antonio, I'll go ahead and hand it off to you. Please feel free to take it away. Everybody, if you don't mind, please mute your mics, just so nobody has a hot mic. That would be great. But yeah, Antonio, whenever you're ready, please go ahead and start.
Hey, thanks for the intro. Hi, everyone. As it was mentioned, my name is Antonio. I'm an independent security researcher, and I'm currently focusing in environment testing, property-based testing, learning like many tools such as Echidna, Medusa, Foundry, Halmos, and trying to help protocols on their test suites. So today I'm going to present a case study of how we use fuzz testing on the eBTC protocol to find some interesting bugs, like confirm bugs from manual audits, and also find some new bugs, and also find some bugs that we thought were issues, but eventually we found out that they were not real issues, but they were rather like some interesting behavior of the system that allowed us to better understand how the system would behave under different scenarios. So without further ado, before I start, just some spoiler alert, eBTC will soon do a contest, and they will open source the code base together with the fuzzing setup, so everybody can review in more depth and also hopefully participate in the competition and help secure the protocol further. I'll present a bit like how eBTC works so that everybody is at the same level. But basically, eBTC was inspired as a fork of Liquidity. So for those who are familiar with it, it's a protocol that allows you to mint a synthetic asset. In this case, it's a synthetic Bitcoin asset by providing staked ETH as collateral, Lido staked ETH. And basically, the protocol will earn a revenue by taking a percentage of the fee, a percentage of the yield from staked ETH. So there are no borrowing fees. And basically, the main unit of accounting of the system is a CDP, a collateralized debt position, which is similar to Liquidity Trove. It will basically track the position's collateral, debt, and also ICR, the individual collateralization ratio, which is basically just the collateral divided by the debt. And each position should maintain a minimum ICR so that it's considered healthy. And so CDP owners, they can open more than one CDP, and each one can have a different collateralization ratio. They can add collateral, they can withdraw collateral, they can get more debt, withdraw eBTC, increasing their debt. They can also reduce their debt by repaying some of the eBTC they minted. They can close the position and repay all their debt for that position. And they can also do a mix of these different operations and adjust the CDP directly by providing some different values. And in order to guarantee the health of the system, there's a liquidation mechanism where basically unhealthy CDPs, meaning CDPs with individual collateralization ratio below the threshold of 110%, they can get liquidated, and the liquidator can take a percentage of the collateral at a discount, so that they are incentivized to do that. And then there's also the recovery mode, which is basically a mode where you incentivize all the CDPs to increase the collateralization. Otherwise, they can also get liquidated if they fall below the total collateralization ratio of the system, which is basically the sum of all the collateral in the system divided by the sum of all the debt. So that's the recovery mode, which is triggered when the TCR, when the total collateralization ratio of the system is below 125%. So there are these two modes, and depending on your collateralization ratio, your position can get liquidated. And there's also a redemption mechanism that was like Liquidity introduced on LUSD, where basically any eBTC holder can exchange their eBTC for a staked ETH, even if they are not, if they don't have any open positions. So they can have this ERC20 token. They can exchange at face value by the collateral of the system, and there's a fee that grows by the number of redemptions that are happening to discourage users from redeeming too much. So this is the basic operations of eBTC, and but you can think of it as basically like a protocol that lets you borrow a synthetic Bitcoin by providing staked ETH as collateral. And yeah, so now let's take a look at how we did with the fuzzing setup, and just so that you know, the protocol already had a very robust fuzzing setup. We just did some improvements and mostly focused on the invariant tests, because all the stateless fuzz tests they were already implemented using Foundry. So we focused more on the invariant tests. And for that, we started with laying down all the system properties. So most of those came from the protocol white paper, or purple paper as they call it. And just by reading the white paper, you can extract many of these properties. And we basically categorize them by the kind of the component of the system. So there is a CDP manager, there is an active pool that tracks the system debt, and so on and so forth. So there are different parts of the system, and we categorize them this way. And also depending on the category of the invariant, because some invariants, they are more like unit tests, where you do something to the system and then you compare the state that was before and after your action. And others, they are more high level. They are generic properties that they must be true at any given time. So this is similar to, like, these high level properties. They're similar to like on ERC20 token, the total supply should always be greater to or greater than or equal to the sum of users' balances, because otherwise, like, you are minting ERC20 tokens from thin air. So this is like all these high level properties. They are very important because they should be true at all times. And these are usually the ones that we're starting, like, by implementing those when we are doing this type of invariant testing engagement setup, because these are the ones that, if they break, then everything is at risk. There is usually funds at risk, and they are very important because you don't want your system to have any accounting mistakes or anything like that. So we created this markdown file. We are tracking our properties and, like, doing them one by one in order of priority. Then we also created some configuration files and some helper contracts that would help us with our fuzz testing. And we were always mindful of trying to reuse the same contracts between Foundry and Echidna, because I'll show it later how we did it. But what we did is basically having like a generic setup function that would basically deploy everything. So we deploy the governance contract, we deploy like the access control contracts and a bunch of other contracts. And we also have some fork setup functions that basically we just copy paste the contract addresses on the like on mainnet or on testnet that we use to do some fork tests. And and basically later we can just extend these setup functions and create different target contracts that will be the subject of our fuzzer, basically. So the fuzzer would just, in the case of like a local test, would call this tester contract. And in the case of a fork test, it would just call this contract. And all our target functions would be the same. They would be implemented on this target functions contract. So this way you can like reuse the same code everywhere with minimal boilerplate and minimal differences, basically. So here there's like a fork tester contract. There is a tester contract, which is the local tester. There are some other contracts that are specific to one component. So for example, for the price feed, since it has many different states, we wanted to have the fuzzer check on each state individually. So we have a specific tester for this one. We also have one for ERC20 properties for the collateral token tester. So basically we create a different tester depending on the use case. But this one here is the one that has all target functions that interact with the eBTC system. So later we create the properties contracts. So there's one abstract contract just hard coding all the properties descriptions, which is just the list of the properties. I think this is useful because it makes it easy to just go there and see what properties are implemented and what they mean. It's also useful for logging. If you just hard code like AP05, later we won't know like exactly what it means. So we also include the description of the property. And and this is the property implementation. So we just like create a simple function that will check for something. So for example, here, the collateral balance on the active pool should be greater than or equal to like what this function returns, which is just like an internal counting variable inside the system. So this should always be true, like no matter what happens in the system. And there are some other invariants coded here. And then we also have like one contract for Echidna properties. I think this can be refactored in like maybe later to reduce the boilerplate, because these functions are the same ones as the ones from before. It's just that Echidna requires you to have a specific like pattern for your its properties. So basically, it starts with Echidna underscore, and then like restricts no parameters and returns a Boolean value. So since these functions, they have some parameters, we thought it would be easier to just like copy paste. But I think you can also like change some configuration parameters of Echidna so that this wouldn't be necessary. Like, but yeah. So this is just like another contract for testing Echidna properties, which is useful on property mode. And this is the contract that we used for Foundry. So this is the Foundry base contract, the base fixture contract for Foundry that is used on other Foundry fuzz tests. So basically, we have like we create everything, like we deploy everything here, and we can do some assertions using Forge STD. That these invariants, they are always true. And we just call this function, ensure system invariants. at the end of each Foundry test, and we're using the same properties that we created for Echidna in Foundry. So it's just like a matter of crafting the contracts in a way that you are using the same properties everywhere. And this is interesting because this was like what happened is that we started. So when I started working together with eBTC, the protocol already had many founder fuzz tests implemented and some Echidna invariants implemented, but they wanted to improve the coverage of their invariant tests. And we did this refactor to also use the same invariants everywhere. And what happened is that it was interesting because when some Echidna functions would break, because we had like the same invariants everywhere, sometimes some Foundry fuzz tests would also break. When initially they wouldn't, just because the invariants weren't being checked against at the right place. So this is why I think it's very helpful to make sure that you are using the invariants everywhere, both on your Echidna test and also on your Foundry fuzz tests. Yeah, so here is is like an example of the target functions contract. This is like the most important part. All the rest is like a bit of like a boilerplate. But right now, this is where you implement the actions of your protocol. So for example, here, this is like a closed CDP. This is like a closed CDP function where you receive a random integer. You have some preconditions that there is at least one CDP in the system. More than one CDP in the system because you can't close the last one. That's one of the assumptions of the system. And then the user that is interacting with this function should have at least one CDP. And then you kind of take the CDP index, CDP ID like randomly, and then you do a call to the borrower provisions contract and call close CDP. You can also do like a VM.prank here. We just did it this way because our actors needed to perform some flash loan actions. So they needed to be contracts complying with the ERC. I don't remember exactly, but the ERC borrower interface, basically. So basically our actors, they are contracts. This is why we just do a proxy call and they are the ones interacting with the target contracts, with the contracts that belong to eBTC. And here we have also some helper functions just to do a snapshot of the state before the call and after the call, so that we later can compare like what state changes happened. So for example, here we fetch the price, the collateralization ratio of the CDP, the amount of debt, amount of collateral, so on and so forth. And then we can compare what changed and what should have changed and what didn't change. So for example, here, when I close the CDP, I know that the CDP debt should have been cleared and should now be zero. So I do an assertion about that. And we are also here interested in the case where success is false. That's also important because if you only check for the happy path, you might be missing some bugs that they are related to like some denial of service issues. For example, if you do all the preconditions correctly and you know that closed CDP should never revert, then you can also check for the case where success is false. Because if this reverted, then that's also very bad because it means that a user cannot get their collateral back. So that's a problem for your system. So it's always important to make sure that you're checking for the success path and also the failure path. Yeah. Finally, this is one new novel approach that we implemented that I think it's very helpful for this type of setup where you're using more than one fuzzer. And I think I shared that in other places, but the reason why we did this way, like why we use Echidna for the invariant tests and Foundry for the stateless fuzz tests, and was because Echidna has better support in our point of view for invariant testing. Like you can check the coverage report of your target contract and make sure that you're getting 100% coverage. Otherwise, you might miss some issues because the fuzzer is not hitting some states. And this is especially true when your contract is very complex. So sometimes if you do just like 10,000 or 100,000 like transactions are run like very short, you might not go into all the different states. So it's very important to like fine tune the number of target functions that you have, the number of input parameters that you have. So all this is only possible if you are able to see the coverage report. And I think like there are other very useful features that Echidna has and Foundry still does not have for invariant tests. So this is why you use Echidna. And I think like Medusa is also another good option for invariant tests. It's still like a newer tool, so it's like being still like needs some improvement, but it's also very good for that. We're currently using all of those, so kind of mixing these different tools because the setup is very generic, so it allows us to use these different tools. But Foundry, on the other hand, it's much faster. So Foundry is super fast. It's much easier to share the test cases. Like you can literally just copy paste the transaction sequences that Echidna found on Foundry, and now you have a unit test. And now you have a broken unit test that you need to fix. And after you fix it, you can also it'll be there forever, right? So if you make any changes, it will run much faster, and it's easier to share with your other developers. So this is why we did it this way. So basically, this Echidna to Foundry contract, this test contract, it inherits from Forge STD test and also from your target functions contracts that it's the same one that I just showed, like implementing closed CDP, for example. So here there are some like random input that Echidna like used to break the invariant, and then we can just replicate by just copy pasting. So this is like the whole setup, and now comes the more like exciting part, which is like how we are able to find these vulnerabilities. And just before I start, one approach that we took when we started this engagement was to do this invariant testing work in like a blinded approach. So personally, I had not read any of the previous audit reports that eBTC had gone through, and we did this intentionally, not to get too biased by the findings that the auditors had found. Otherwise, I could just like I don't know, like be very specific at the issues, at the specific issues that I was trying to find, and lose track of the big picture, because usually the general invariants, they are more they are I think they will sometimes catch different issues for the same broken invariant. While if I was targeting, like if I had read the audit report, I'd be too biased and trying to catch a specific issue. So this is why we did this blinded approach. So I didn't read any of the audit reports until kind of maybe like in the middle of the engagement, when I had already like implemented a bunch of invariants, and we were trying to fine tune the tool. So this was an interesting one where basically this was flagged by a Spearbit audit. It's a high risk vulnerability where basically the CDP could be inserted in a wrong position, in an incorrect position of this sorted list. So there's basically a data structure inside one of the components where they maintain a linked list of sorted CDPs. And this is very important because if the list is unsorted, then wrong CDPs can get liquidated. Like not necessarily the most risky, the riskiest CDPs can get liquidated depending on how you call the system, or maybe the healthiest, like not the unhealthiest CDPs can get redeemed against. So it's very important that the sorted CDP linked list is in the correct position. And there was basically, yeah, so the root cause of this issue, it's a bit, it's not very simple to like explain here in a very short time. But the root cause of this issue was because it was because of like an inherent difference between eBTC and Liquidity LUSD, which is Liquidity uses only Ether as the collateral, and eBTC uses stake Ether. So there are many different methods included, and some different implementation details related to accruing, to getting the accrued staked ETH from staking, basically. So yeah, so basically, depending on how the system would do this internal accounting or this synchronization mechanism, sometimes things could go wrong, and this is what happened. And basically the team, Spearbit found the vulnerability, and the team fixed it by, the team fixed it by making sure that the global index of STE was up to date before any operation. So they included this kind of synchronization call here before any operation. And basically, like this was the fix. And we also found this same issue just with like a very simple invariant, which is that the linked list should always be in order. And so the first one should always be higher than the second one, so on and so forth. So we created these two invariants, and they broke very like rapidly when we started implementing, and we had already 100% coverage for the target contract. And this is like a bit of our process of debugging, because usually it's not very evident the root cause of the issue. Like, you know that the invariant broke, but then you have to debug why it broke, and you have to like create a unit test preferably so that you can create some logs and so on and so forth. And this is like one example of our conversation where basically we found that the issue would go away if we would manually synchronize the internal accounting system for staked ETH. So basically by calling that manually, we would make the issue go away, and the linked list would always be in order. So like we eventually debugged it and found that was the root cause, and how to properly fix that broken invariant. And so this is the second one. This one was from a Cantina audit, which is basically another high risk issue related to opening dust CDPs, dust positions. And these dust positions are positions that have a very small collateral, very low collateral value. And that's bad because then, depending on this position, it may not be profitable for liquidators to liquidate these positions, and they can just stay in the system kind of forever, like as a bad debt. And so there's a minimum collateral value on the system, and it should never break. And basically, the developers had a check implemented to make sure that you wouldn't do the synchronization unnecessarily. That was, I think, the idea behind the condition, but that was not implemented correctly. And we were also able to find the same issue with a broken invariant, and the invariant is basically that CDPs should always maintain a minimum collateral size. So that's one of the very basic invariants. that's kind of written everywhere on the white paper. So we implemented that one, and Echidna found a sequence related to negative rebase, and eventually we found that the if clause was wrong and was not causing the synchronization to happen when necessary. And so that was another one. And now this is one example of a new bug that we found with the fuzzer. And this one was not kind of missed by any of the audits, but was instead a bug introduced as a fix for an issue of an audit. And I think this is fairly common. And maybe like that's sometimes scary because not necessarily the auditor kind of, if you implement a fix, not necessarily the auditor will review your fix with the same, level of detail as the initial review, just because the fix review is like they usually have a shorter time frame, or maybe like they'll just like make sure that you fixed what they flagged, but what if you introduced another bug? So I think that sometimes happen, and that I've seen some instances of this happening in live protocols where the protocol implemented a fix and then introduced another bug by accident. And so this is an example where we were able to find it with the invariant tests. And this was actually a very severe bug where basically you were able to liquidate healthy CDPs. So if you can liquidate healthy CDPs, you can like basically make a lot of stress into the system, where you can basically force it to be more and more unhealthy. And the bug was a very simple logic issue where there is a single require statement, and then as a result of a refactor, it was broken into an if-else clause, and one of the branches of the if-else clause was implemented wrong. So so we found it with the invariant and later fixed it. And there was also a new bug that we have that hadn't been flagged in any of the previous audits, but it was more like maybe a medium severity issue, not a critical one, which was related from the mismatch between the internal accounting system and the external view functions. So the problem here was that because eBTC has this internal accounting system that needs to keep track of ST index, basically, depending if the internal accounting index is up to date or not, it will report a different value from the view functions. So that's the root cause. And the problem is that we found that some CDPs could be liquidated even if they were considered healthy. So like if they were considered healthy through the view functions, but in reality they were not unhealthy. They were not healthy. In reality, they were unhealthy, but the view functions were reporting them as healthy. And the reason why the view functions were wrong is because the view functions wouldn't do all the updates, like the state changes for the state index. And as a result, like consequence of this mismatch is that you could have maybe some users of the system, they would think that their CDPs are healthy, but in reality, they are not. Like a liquidator can just call the liquidate CDPs function and liquidate their positions. Because by calling liquidate CDPs, you would execute the sync mechanism and then update the state, and maybe the CDP would get unhealthy as a result of your liquidation. So because of this mismatch, it actually like triggered a whole bunch of kind of like next tasks within the development team of making sure that the view functions they were trying to report the correct value. And all of this can be simulated. Like if you are an external actor and if you are a user of the protocol, you can simulate. You can do the simulations. You can kind of like guarantee that the actual state is the one different from the view functions. So the view functions were not reporting the most up-to-date value, but that can be confusing. So the team implemented some lens type of contracts, some quoter type of contracts that they basically do the operation and they can kind of return the updated value so that users can better understand like the real state that depends on staked. So this was like a main difference that we found. And like in the end, this was not like a bug inside the liquidation function. It was rather a difference from the view functions. And this was like another interesting one where we found like a bug, but in the end we found out that this was not a bug. It was the expected behavior of the system. But I think this shows how fuzzing can also help you better understand the different behaviors of the system under different conditions. And this is something that's very difficult to do just by, by thinking about it beforehand, because it's very hard to think about all the different possible states. So many times the fuzzer will come, will show you a sequence of transactions that get to a state where you weren't thinking about, and maybe it will break our invariant, and maybe it's not a bug. Maybe it just means that your invariant is not correct, or maybe it's not as complete as it should be. So here one example was this invariant of TCR, so the total collateralization ratio of the system should increase after a liquidation. So this was, so it's like, it looks correct. Like, okay, so if you're liquidating a bad position, an unhealthy position, you should improve the health of the system. But the problem is that we later found out after many like discussions and many like tests, many unit tests, that this was actually like an expected behavior. So sometimes the TCR can decrease, and the point is if there is redistribution of bad debt. So basically what happens is that you're always incentivizing the liquidator to take an unhealthy position out of the system. And because the liquidation has an incentive, so the liquidator is incentivized to liquidate, the liquidator will take the whole collateral of that unhealthy CDP, but it will leave part of the bad debt. And the problem is that this bad debt, it will actually lower the TCR, and it will lead the system to like a worse kind of state than it was initially. And we discussed like how this was like an expected behavior of the system, and this was actually like a tough choice. Like if you think about the point of view from the system, because if the CDP is unhealthy and you leave it there, it will like it will never get out. So so like incentivizing the liquidator makes sense in this case, and so this like creates like a discussion of what happens when you are under bad debt and the liquidator will take away some of these CDPs. And this is one of the examples that sometimes is useful to like think mathematically and do some, maybe calculations symbolically, because you can find that some of your assumptions, they are not correct. And like thinking about the expressions of your invariants, they may help understand why something is failing when it shouldn't, or maybe something maybe something is failing but it should fail, and you need to update your test. So basically what we did here, like as a result of this non-issue, was that we updated the invariant and we just had like an if else. So like if there was a redistribution of bad debt, then like check for another invariant. But if not, then this should always be true. And then like the test would pass and the fuzzer wouldn't find other instances of this problem. Yeah, and I think that's about it. So we found some quite interesting issues and improved a bit the test suite of the protocol. There were all other like smaller or minor issues that we found, but I didn't include them here not to take too much time. But if you are interested in discussing this more further, please feel free to reach out. I'm happy to help, and that's it. So I think I'm open to questions now.
Yeah, fantastic, Antonio. Great seminar. Yeah, there are a few questions. If you go ahead and look on the comments tab
Yeah.
that we showed, you'll see some folks, believe starting from Fran, and then you can work your way down.
Yeah, so I'll read it out loud. Does fuzzing-based coverage works the same as usual tests? I'm not sure I understand. What do you mean the same as usual tests? Can you clarify the question? I think like, do you mean if the coverage report would show like the covered lines in green and the ones not covered in red? Is that the question?
Yeah, Fran, if you want, feel free to unmute your mic or drop some clarity inside the chat section.
I think he's not here anymore, but I'll try to answer like from what I understand. So yeah, basically, like the coverage, kind of the coverage report is the same idea. You are always trying to look into what lines and what branches of your target contract were hit, and based on that, you kind of infer which states were tested by the fuzzer and which weren't. So we had a problem with that when we started working with the fork tests. And the problem is that the fork tests, they take much longer to execute. And I think it's just maybe because of the RPC calls that you need to perform over the internet, but they are usually slower. And as a result, like by the same amount of time, we were having a much lower coverage than using our local tests. So, and we were able to see that some of the different states of the system weren't being hit. So, for example, like in eBTC, you can, let's say, like there is a recovery mode. Like that's one example. Like when the TCR is lower than the critical polarization ratio. And we have some invariants that they check for recovery mode. And by looking at the coverage report, we could see that those lines were all red, so they were not. So the fuzzer was not hitting those lines. So we were sure that particular state was not covered by the fuzzer. And what we had to do was basically just like so we reused the corpus of the local tests on the fork tests, and with that. So since the fuzzer had been already able to find all these different states, it did the same kind of state exploration, let's say, as the local tests on the fork tests. So we were able to test that also on the testnet. So I think that was the question, and this is usually how we do that, to debug and make sure that the fuzzer is actually testing what it's supposed to test. Okay, question number 2. Do more invariance checks cause a kidnap to be biased and lose some? Okay, as in one invariant, many BCS. What's BCS? Many. Okay, so one invariant, many or invariants, one piece maybe. Okay, if you have time, or we'll keep them miss some combinations. Yeah, so this is an interesting question. So maybe how do you balance? So let me rephrase. How do you balance between adding more invariance checks um, or not? So what happens? So because fuzzing is a random process, there is some sort of kind of bias that the fuzzer can get, and what's the name of it? I forgot the name, like the technical definition of this process. Yeah, I think it's saturation or something like that. But basically, after some time, the fuzzer will kind of stop finding new interesting states and increasing the coverage, which it uses to guess the next input values. So there are some studies on Web2 fuzzers related to that. I haven't found any studies about that for Web3 fuzzers like Echidna or Founder, but that's definitely an interesting thing to understand. And this is useful because as a protocol, you need to decide when to stop running the fuzzer. So maybe after 1 hour you didn't find anything, should you keep running it? Or like maybe one day are you like happy with it? So when do you stop? And I think some studies exist for Web2 fuzzers that maybe help you decide when to stop, and which is basically when the fuzzer stops finding new stuff. But I think like the biggest question about this optimization from our point of view is deciding on the number of target functions that you implement and also on the number of inputs that you implement. Because sometimes if you like implement a lot of different functions, the fuzzer will basically like probabilistically will call each one of the previous functions fewer times, like during the same amount of time. So you should either increase the duration of your tests or or basically like if you keep the same duration, it will basically have a lower coverage. And that happens sometimes. So you should always take a look at the coverage and see if by introducing a new feature, for example, if you want to test a new function, you may like make all the others worse, essentially, like by fixating the same amount of time. And that's the realistic scenario, right? Because you aren't usually testing for a whole week. Maybe you can, but usually you let it run over like some time, some duration, and then kind of stop it, and you do this iteratively. So so we saw this happening on eBTC, like when we implemented some new functions, we would see the coverage kind of drop for the duration that we were testing. And we had to decide like what features we wanted to test for the same time, or we would need to increase the duration of the tests. By the way, sorry, there's another like thing that I think is worth mentioning, which is like about this maybe like random nature of the fuzzer and the saturation. Like something that we also noted, which is I think there is also some papers about this, which is sometimes running the fuzzer like in parallel with different seed values is better than letting it run for a longer time with just one instance. So, for example, let's say you're running your fuzzer on AWS. Maybe it's better to run 10 different virtual machines or like instance of your fuzzer instead of letting one instance for 10 times the duration. And that's because the initial states, they can influence the likelihood of you catching the bug, or maybe like the probability rather of you catching a bug. And we also found that happening. So basically, we ran in parallel 6 instances for eBTC at one point in time. And And then we let it run for 24 hours, or not 24, for 12 hours. And after 12 hours, 2 instances had found nothing. One instance had found one bug, another instance had found another bug, and I think like the other one had found 2 bugs. So it's kind of like it's not like deterministic that you can just increase the size of your machine and get better results. So I think sometimes it's worth testing in parallel different runs. And Echidna even has a tool for that, but I think it's like experimental. They call it Echidna Parade, where basically they would try to optimize for the number of target functions called. So if you have like 10 target functions on your contract, they will maybe like run one sub-process calling 5 functions, another one calling 3 functions, or maybe like 5 different ones, and so on and so forth. And they will combine the corpus and like merge everything that these different sub-processes learned from it. But personally, I've never used the Echidna Parade. I've only read the paper, and I'm not sure if it's like as widely supported as the Echidna. But yeah, this is something that you should be mindful of when you are working with fuzzing. And then there's I think the last one, quick question. How do we ensure that you have tested all the invariants and not missed one? So I think like this is a bit related to the coverage question. So there are 2 parts. Let me see if I understand this correctly. So the first part is you actually implemented all the invariants. So right now, for example, for eBTC, we have listed maybe, I don't know, like more than 50, I don't know, maybe 18 variants, and we have not implemented all of them just because there are so many, and I don't know, it takes time, and you're usually prioritizing on the most important ones. So if the invariant like isn't there, it's not being tested. But sometimes the same state is being tested by a different invariant, so there is some overlap. So this is why you usually start with the most like critical ones. And so kind of we start with the most important ones, and then there's the second part of making sure that the invariant was flagged. Was reached. So that part of the code was reached by the fuzzer, and this is how the coverage report is very useful. So you need to make sure that all you're having like green lines everywhere, and all your branches are being hit, and then it's kind of like a matter of time to have it find maybe like a combination of values and transactions that will make that invariant break. There's another question. Okay, question from Alex. How would you test for scenarios? So give Echidna a new setup and check for specific invariants. Yeah, so this is an interesting one. So there is one a very good video like from Trail of Bits on Echidna, and what they have is basically the initial state being set only once by the fuzzer. So you basically create a simple like init function or maybe setup function that instead of deploying all the contracts, you also, for example, mint a different number of tokens for your users, and then you use that as the initial state. So that's sometimes useful because depending on the initial state, some bugs can be triggered and maybe not. And so maybe a bug will only happen if you, I don't know, like increase the collateralization of the system by a lot, and maybe the initial state doesn't have that much collateral or something like that. So I think that's a way you can do it. But yeah, so maybe like trying to create different states in the beginning of your first function call from Echidna or from the fuzzer. Question: how do you run the fuzzing campaign? Have you used Echidna Parade? Can you clarify what do you mean by running the fuzzing campaign? Do you mean like these different kind of running different jobs for to try to go through different transaction sequences? Is that it? You mean run the fuzzer? Well, so what we have is that we have some basically we have like this combination of contracts, and we have some yard like npm scripts that we just basically like hard code all the parameters that we are interested in. And since we did it in a way that like the contracts will work for any different fuzzer, we can just do, like in the case of eBTC, we do like yarn echidna or yarn medusa, and you run the different fuzzers. So yeah, it's just a matter of like the configs on sequences and so on. Sorry, I'm not sure I understand. Like, do you mean the different configurations? Is like about the second question about Echidna Parade? No, I've never used it. I only read the paper where they presented it, and I found it very interesting. But I'm not sure there's enough usage because the repo is a bit old, and I think it was done as like a dissertation or thesis from someone from Spearbit's team. So I'm not sure if it's being used in like real projects like production. So I'll ask the question from Alexander and later. Okay. So what configs we're using with Echidna in terms of fuzz runs and sequences? Yeah. So we are. So we have different configurations either for local tests or for cloud tests. So for the local tests, we let it. Yeah. So for the local test, we let it run for usually 100,000 sequences, transactions, and I think we let the max depth or the number of sequences as the default, which I think it's 25. Not sure. Yeah. So that. No, it's 200. Yeah, we let it as 200, and the test limit as 100,000. And then we have some cloud tests that we run on AWS, and we use 300,000, which like empirically we verify that it's usually 24 hours. So we are more like limiting by the number of hours. We do like our work, we finish our day, and then we let the browser run, and we get back tomorrow and see what it found. That's how we're usually doing it. And okay, so question about Alexander from Alexander: How would you approach setting up fuzzing when there is a red product state on the first surface? Any grouping rank in terms of which functions are invariants to have priority? Yeah, so I think like I'm not sure like specifically what would be the example you mentioned about a very broad external surface, but I think it makes sense usually to start with the most high level ones, like the ones that if they break, then everything like is like everything went wrong. So for example, no user should ever like I don't know like lose funds once they deposit or something like that. I think like these ones are great because you might not find the root cause very easily because since they are so generic, it takes more time to understand what caused them. But I think they are more useful for you to get confidence in the system. And and I think that this is like what this is about is for you to like assess like how the system is behaving under different transactions. So if your most core invariants are okay, then you're like more you're more confident on it. And I think that's it.
Yeah, I think we're good to go, and we're just about approaching time. But yeah, once again, Antonio, just wanted to say thank you. This was a fantastic seminar. think everybody really enjoyed it, and thank you to everybody that asked great questions. We will be posting this hopefully publicly today. So there will be a recording posted, so anybody that needs to reference it will be able to. But yeah, again, fantastic seminar. And just a quick thing for everybody else. If you're interested in doing a seminar, please feel free to reach out to me. I think it's a great way, again, to get your name out, to post about ideas that you want to talk about and get more traction across the community. So if you're interested in doing a seminar like this, or you have ideas that you want to talk about, please feel free to reach out to me over Discord, and I'm happy to get things sorted. But yeah, again, thank you so much, Antonio. Appreciate your time.